And a good part of the work was done by Luis Canonico, who is presenting his thesis today in a few hours. So more details about the results can be found in these 3 articles that are also on arXiv. So before I go to the main topic of my presentation, a little bit of an advertising. So for many of the numerical calculations I will show here, we are adapting Kite, which is an open source software for quantum transport that we launched recently. I'm part of this team. And it uses Chebyshev expansions to calculate response functions in real space, tight binding Hamiltonians. Not all my results are in real space anyway. And also the band structure calculations and the inputs for Kite are made with PyBinding, which is a tight binding package for Python, and it's quite nice to play around. So let's begin with Orbitronics. And the idea is the following. The manipulation of orbital angular momentum of light, it's quite an old subject of investigation with more than 20 years. And there are several applications for that nowadays, at least suggestions of applications. However, the manipulation of orbital angular momentum in solids is more incipient. There have been works on the subject floating around for some time now, but without getting a real critical mass. And the idea behind Orbitronics is the manipulation of the orbital angular momentum in solids, as the name suggests. But the question is, why do you want to manipulate the orbital angular momentum if you already manipulate spin, right? Well, in spintronics, as we've been discussing all morning, we need either magnetism or strong spin-orbit coupling to generate a spin current, which of course will limit the number of materials that can be used for this. And on top of that, if we begin to discuss about surfaces, which is the case of 2D materials, it's already known that orbital magnetism is enhanced in surfaces. And this suggests that the other orbital effects might be quite relevant in 2D materials. So the idea that I would like to discuss here is the possibility of manipulating orbital angular momentum in a more diverse pool of 2D materials. Well, as I said, it's quite incipient, but there are some activity on this field, especially lately. Well, it all began with some works from Jin-Hong Park that discussed that orbital Rashba effect is a genetic feature of surface bands, and that can be measured by circular decoys. And then it was measured in some materials, I will discuss it later. And similar to the spin counterpart, it could be important for the generation of orbital currents. So talking about orbital currents, in 2005, Burr and Vig and collaborators made the first proposal of Orbital Hall effect in silico. And there were other theoretical works in 3D metallic systems. There are also some theoretical proposals for the equivalent of the Rashba-Eldenstein effect for orbitals, orbital angular momentum. And more recently, there was a first proposal of using orbital torques to switch the magnetization in ferromagnetic layers. And in the last 2 years, a few experiments on orbital torque in metallic multilayers, and many times using a material with very weak spin-orbit coupling, like copper, for example. And of course, this is getting, the orbital effects are getting more important with twisted graphene bilayers and the recent characterization of cherry insulators that are originated from orbital magnetism in graphene twisted bilayers. Well, but the focus of my presentation is the orbital Hall effect, which is basic and analogous of the spin Hall effect. So in the spin Hall effect, if we apply an electric current, current in one direction, electric field, sorry, in one direction, we're going to have a spin current or a spin accumulation of opposite spins at the edge that are perpendicular to the field orientation. With the orbital Hall effect, it's exactly the same thing, but instead of the spin currents, we're going to have an orbital angular momentum current. And the calculation can be made in a similar way. We can use Kubo formula, but also we can analyze the orbital Hall effect in terms of L projected direct curvature. I'm not discussing this here, but just letting you know that. So in 2008, 2009, there were a set of works showing that several metals presented orbital Hall effect. And more recently, Lee's group that has several works on this subject showed that even metals with very, very small spin-orbit coupling, like aluminium, for example, can have a strong orbital Hall effect. But more importantly, they linked the existence of the orbital Hall effect to orbital textures in these materials. And orbital textures, different from other orbitronic effects that I was discussing before, are quite known in solids, and they were observed in several different materials. So, for example, it's quite well known that there are orbital textures in topological insulators, in K-space. Oops. Sorry? Well, my keynote, sorry guys, my keynote was lost here. Let me stop the sharing, stop sharing. Can you hear me? Hello?
Yeah, we hear you.
Okay. So I only, just 1 second, because I totally lost the keynote was broken. Just 1 second.
Okay, no worries.
Let me try to go back to where I was before I start sharing again. So, okay.
Good.
Can you see it again? I was probably right.
Yes.
Okay.
Yes.
Sorry about that. So, so not only in topological insulators, but also in 2D electron gases in the interface of oxides, or new, they're suggested to exist in novel 2D materials like borofin, for example. And they were also observed in real space in tantalum-based 1T TMD layers. So if we think that orbital textures can be connected to the generation of orbital currents, that might be plenty of different materials to try this out, right? So let's try to see the orbital Hall effect in the simplest possible model. And we are particularly interested in orbital Hall effect in 2D materials. So let's consider the minimal model for 2D materials, but this model needs to have more than one orbital. It has to be multi-orbital, so it cannot be, for example, graphene. But this is probably the analogous of graphene for multi-orbital systems. And the use of this model was first motivated by experiment in single layer of bismuth atoms, at least for us, but now we discuss it in the concept of orbital Hall effect. So in search of the quantum spin Hall insulator, which is a topological insulator in 2D, Klassen's group was able to grow a single bismuth layer on top of silicon carbide. So bismuthine normally is a buckled structure, but when grown on top of silicon carbide, there is a little bit of strain in the system. And so the layer is flat, as can be seen, for example, from STM measurements that confirm like the honeycomb structure. And first principle calculations show that this single layer, if we do not consider spin-orbit coupling, has a band structure that looks very much like graphene with a Dirac cone, but the electronic properties at the Fermi level are dominated by px and py orbitals, while the pz band is well below in energy. So there is a paper from them from, I think, maybe today, and they analyze the correlations on this system. I just saw this, so this is why it's not in my presentation, but let me record that there is a new paper from the same group on the same material, but analyzing correlations. So, but this simple model that only contains a honeycomb lattice with px and py orbitals has been around some time. Wu has several works on this Hamiltonian and for other systems. But so we have the hopping between these orbitals, and I'm using the basis of the eigenstates of LZ. And then there is another term that takes into account sublattice symmetry breaking here. And finally, a term that can be a spin-orbit coupling, but it's an on-site term, so it only connects states in the same site. Or if it's a spinless system, we can think that this is also could be seen as an exchange term or a Zeeman-like term for the orbital angular momentum. Well, this is the structure without spin-orbit coupling. When spin-orbit coupling is taken into account, different from Kane and Mel's model, as I told you, LZS is connecting the two orbitals in the same site. So the spin-orbit coupling is very strong. And therefore, the generates spin state split, and each band will have a spin charge number, which means that this is a topological quantum spin Hall insulator. And if you look at the nanoribbon, there are counter-propagating spin resolved edge states in a system like that. If we consider this type of exchange interaction, this is just basically a orbital channel insulator. So we can think about these two different limits. Well, similar to Kane and Mel model, if we break sublattice symmetry, the system can undergo a topological phase transition. Here I show the longitudinal conductivity in green and the spin Hall conductivity in black, and we can see three nice plateaus. So, and if we look at the nanoribbon band structure, we can see edge states in these three gaps. So it has a three nice spin Hall conductivity plateaus. And if we keep increasing sublattice symmetry breaking, eventually this central plateau is destroyed, like in the case of Kane and Mel, but we still have two lateral plateaus. Well, but in fact, the topological phase diagram of this simple model is quite rich, and it's richer than the Kane-Mel model, has more topological phases. The phase diagram is here, and there are possibilities depending on the ratio between not only lambda and VAB, but also the hopping. So we discussed these two limits in the previous slide, one for VAB much smaller than lambda, the opposite limit, but when we have the two contributions, it's possible to have a third phase. Well, the central plateau is not destroyed, and we have edge states crossing the main gap, but the lateral plateaus are destroyed, and this is the phase that I will also discuss. I will discuss these three phases here. Well, up to now, we only talked about the spin properties of this model, which are interesting for Orbitronics, but we need to discuss the orbital aspects. And the first question, I think, would be, does it have orbital textures, for example? And the answer is yes. Of course, we cannot define, we only have px and py orbitals, so we have a restricted Hilbert space. We cannot define the algebra for L1, but still we can define spinors, and in this reduced space, this spinor has a texture that's presented here. And if we notice, the color indicate the LZ orientation, the out-of-plane orientation, and the arrows are the in-plane texture. So the in-plane textures close to K and K prime, they look very much like vortices, anti-vortices actually. and close to gamma points, it's like a double vortex. When we break sublattice symmetry, the out-of-plane contribution changes a lot, but the in-plane is more or less the same. Oops. Sorry. It's okay. So it's my keynote is having some issues. So, well, even in the absence of spin orbital, the thing that's interesting about this model is that even in the absence of spin orbit coupling, the model presents orbital Hall effects. There is a degenerate point where we cannot calculate these orbital textures, but all over the rest of the Brillouin zone, we can also see the same textures. And we can show that here I show the band structure without spin orbit coupling. When we break and we don't break the sublattice symmetry, and the structure of the orbital Hall effect is more or less the same. So there is an onset of this orbital Hall effect that begins to appear when this in-plane orbital texture begins to be felt by the electrons. So this is very similar to other systems where you can have orbital spin Hall effect with spin textures, for example. Well, when we take the spin orbit coupling into account, of course, we have now, if we don't break sublattice symmetry, we have degenerate states. And if we look at the textures of spin up and spin down agent states, we see they are very similar, but the LZ orientation is opposite. So if we consider the two states, we don't have a LZ contribution, but the in-plane orbital texture for the two spin contributions is exactly the same. So this one survives and is the one responsible for the orbital Hall effect. We can also write a low energy Hamiltonian for this system. And if we do so, close to K and K prime, we see that a Dresselhaus-like Hamiltonian can describe these orbital textures quite well around K and K prime. Okay, let's see what happens now with the orbital Hall effect in the three topological phases. So let's begin with the one that we know the most. So we have, basically we only have spin orbit coupling, VAB 0. So the spin states are degenerate. And the spin Hall effect presents three nice plateaus. If we look at the orbital Hall effect, first we see that it's an odd function, different from the spin Hall effect. And because an odd function, it goes to 0 at the central gap. And this can also be seen because these in-plane textures will get canceled if we consider the two lowest bands, for example, will be compensated. But if we look at the lowest band, this is the texture that we have. And the orbital Hall effect begins to increase exactly when the electrons see these in-plane textures. And it has a nice plateau, but this plateau is not quantized. So it depends on the parameters of the Hamiltonian. If we now move to a second phase, now let's break the sublattice symmetry. In a way, we destroy the central, the topological gap, the central gap. We don't have the central plateau, the spin Hall effect plateau. But if we look at the lateral plateaus for the orbital Hall effect, they are still there. In one side, they are in opposite. They are opposite to the spin one, and the other one they are the same sign. And again, they vary with the parameters of the Hamiltonian. And probably the most interesting phase is this third one, because in this case, we break sublattice symmetry, but we have strong spin-orbit coupling. And the central plateau is there. We see the edge states for the central plateau, but the lateral plateaus for the spin Hall conductivity are gone. But surprisingly, we still have an orbital Hall effect. And these two lateral plateaus. These calculations were done in K-space, but we also repeated this in real space with disorder, and this is quite robust against disorder, and can also be understood if we look at the LZ projected baroque curvature. So the LZ projected baroque curvature, the sum of the integration of this can give information about the sign of these plateaus and everything. Okay, so it's interesting. We can generate orbital Hall effect in a quite sizable orbital Hall effect in a 2D material, even in the absence of spin-orbit coupling. But if the orbital textures are present in other systems, as I was discussing before, let's try to see if we can observe orbital effects in other 2D materials, and let's see what happens in materials that were extensively studied, both theoretically and experimentally, like Tmds. So let me discuss now what happens with the orbital Hall effect in Tmds. When I'm saying Tmds, I'm considering a single layer of a Tmd in the well-known structure of 1H, like MOS2, for example. It's a honeycomb lattice, and the transition metal atoms are located in one sublattice, and the chalcogen are symmetrically located in the other sublattice. And we know that this type of TMD presents spin valley locking, which is ideal for the optical manipulations, but does not have a topological phase. And there is a very simple model for this system, which works quite well, which is a 3-bands model that consider only the 3 different orbitals of the 3D orbitals of the transition metal atom, these 3 orbitals. And in this basis, the LZ can be written like this. And of course, again, SZ is a good quantum number for this situation. And the spin orbit coupling will have a similar structure, with different signs for different spin orientations. Well, the band structure, I'm plotting here the band structure of this model for MOS2 with and without spin orbit coupling. So this is without spin orbit coupling. And so we can see the 3 bands. And on the right, I'm showing the orbital textures for these 3 bands. If we look at the valence band, it is quite clear that even with 0 spin orbit coupling, there is a very strong orbital valley locking in the valence band. So the colors here indicate the LZ projection, and the arrows are again the in-plane contribution. And again, we have something like an anti-vortex structure for the in-plane contribution that maybe you cannot see from here. But the out-of-plane contribution is clear, and this orbital valley locking precedes the spin valley locking. So in fact, we can understand the spin valley locking in TMDs by coming from the orbital valley locking in these systems. And in fact, when we include spin orbit coupling and we have this splitting of the 2 spin bands, the orbital texture is more or less the same for the 2 cases, right? So and we know that there is this orbital. Of course, we're going to have something inverted for K and K prime because it's red and blue for K and K prime. But the structure is more or less the same. For the other bands, of course, for this band, which is dominated by L equals 0, the orbital, without spin-orbit coupling, we don't have close to K and K point, we don't have any LZ projection, not even in gamma. And when we include spin-orbit coupling, then gamma gets L polarized. But what happens now if we check the, oh well. Sorry about that, just keynote. Okay, let me try to go back an extra page, okay. So what happens if we now include the orbital Hall effect calculation, and now I'm using this orientation so we can compare with the band structure. We see that inside this main gap, we have a nice orbital Hall effect plateau, and in fact we had orbital Hall. The orbital Hall effect, it's way stronger than the spin Hall effect. That's just the red curve here. If I could show the system without spin orbit coupling, you see that the orbital Hall contribution is more or less the same with or without spin orbit coupling. Here, we can see this in a nicer way. I'm comparing two different materials with different spin orbit coupling. So, of course, this material has strong spin orbit coupling, and the spin Hall conductivity is more pronounced. But if we look at the orbital Hall plateau, it's more or less the same. It's very similar. So this is dominated just by the orbital textures that are very similar in the two different cases. Of course, I could think that I'm always discussing a restricted space. I'm not considering all the different orbitals in the system. So you could think that maybe this is why I get this the strong orbital Hall effect and these plateaus. So of course we had the same questions, and so we considered first principle Hamiltonian of a TMD system, in this case MOS2, and we used Van Yen 90 to write an effective tight binding Hamiltonian for this system that takes into account spin orbit coupling, so it can have up to 20, I think we consider 22 orbitals here. And by doing this calculation, I'm comparing the tight binding Hamiltonian, the band structure of the tight binding Hamiltonian with the first principle calculation. So we have a nice fitting here. And if we calculate the orbital Hall effect, of course, it's more noisy, you have more bands here, but close to the main gap, we have a very similar structure with this nice plateau and some of the same features we see in the 3 bands model. So to conclude, we can see that these metallic multi-orbital 2D materials can host very large orbital Hall effect, even in the absence of spin orbit coupling, and can also, even in insulating phase, they can host orbital Hall effect. Still, these orbital Hall plateaus are not quantized, so they depend on the details of the Hamiltonian. And this orbital Hall effect can be used, for example, for orbital torque transfer. So the idea of this work is just to bring attention to the existence of orbital effects in 2D materials and the potential to use these orbital effects for orbital transfer and then spin transfer or orbital torque and spin orbital torque. Okay, thank you very much for your attention.